Well, let's start our lesson. Uh, Yesterday we have seen this problem. And we have done first part of this problem. Sorry, someone is writing. Okay. Well, we have done the first part of this problem, which is we have calculated time averaged pointing vector. Now, we need to show that time averaged pointing vector is equal to this expression. Will be equal to this expression, and the expression is so P equals time averaged pointing vector equals 1 over 2 the real part of H, no, not H, but E, yes, E cross H complex conjugate. Okay, so let's write quickly what was our E and what was our H. So E was equal to E. Yep, E was equal to E real plus J E imaginary and H was also equal to H real plus J H imaginary. Of course, yeah. Of course, we need to write in phasor, and we need to add j omega t and e to the power of j omega t. So, first of all, let's see what is the complex conjugate of H. The complex conjugate of H is HR minus J H imaginary of e to the power of minus j omega t. Minus j omega t. And now let's take the cross product of E cross H. So E cross H complex conjugate and E cross H complex conjugate. E with we said E is equal to ER plus J E imaginary multiplied e to the power of j omega t, e to the power of j omega t cross the complex conjugate of h is this, and hr minus j h imaginary multiplied e to the power of minus j omega t. So this will be equal to how do we calculate this expression? E to the power of j omega t multiplied e to the power of minus j omega t simplify each other. This and this simplifies, and what we get is ER cross HR. So ER cross HR, or real part of E cross imaginary part of H, real part of E cross real part of H, plus J multiplied by J is minus 1, J multiplied by minus J is plus 1, E imaginary cross H imaginary, okay, cross H imaginary, plus we have plus we have J E imaginary H real plus E real H imaginary. E imaginary cross imaginary cross H real plus, or sorry, minus H imaginary. Okay, so we have computed this expression, or E cross H complex conjugate, and is equal to this expression, and here it is the real part, and here is the imaginary part, and we are saying that we want to show that time average pointing vector is equal 1 over 2 1 over 2 multiplied real part of E cross H complex conjugate. So if we write 1 over 2 and we said a real part of this, or real part of this number is this here, we may see multiplied, so ER cross HR plus EI cross HI, or so we have written it in this form, ER cross H R plus EI cross HI over 2. So this expression is equal to this expression, and the last expression in turn is equal to the time averaged pointing vector which we have computed yesterday. Exactly this vector. Okay. So now we move to the new topic. So it is so it is a new concept, but not new topic. New concept of this topic: a complex pointing vector. So, as we have mentioned earlier, as we have mentioned in previous lessons, most electromagnetic relations encountered in our course, and also including most of the applications in practice, are handled in the frequency domain, assuming sinusoidal excitation. Therefore, it often becomes necessary to define the pointing vector in frequency domain. This definition also shows a relation between real and reactive power and is closely related to time averaged power. Okay, in previous example, in this example, we have defined that time averaged pointing vector is equal to the 1 over 2 of real part of E cross H complex conjugate since the fields used to find this relation were completely general phasors. This relation applies for any sinusoidal fields. Complex point and now we may define the complex pointing vector as okay, P C, which where in this index C stands for complex. Okay, a complex pointing vector can be defined as E cross H complex conjugate, or vice versa, E complex conjugate cross H. Well, unit of measurement is always watt per meter squared. Here is also watt per where okay, here E and E and H are phasors. Okay, so before going on, we may also discuss the formal derivation of complex Poynting vector. For derivation of the expression for complex Poynting vector, we of course use Maxwell's equations. Okay. Okay, we use first two Maxwell's equations in frequency domain, which are the rotor of E was equal to j minus j omega mu h, and the rotor of H was equal to j plus j omega okay, j omega epsilon E. And if we want to write the conjugates of these two equations, what we have, the conjugate of first equation will be plus j omega mu h conjugate, and the conjugate of the second equation will be so j remains the same minus j omega epsilon E conjugate. No, j is also complex, and from the definition of j, we may define the complex conjugate of j, and it is equal to complex conjugate of j0 plus complex conjugate of j e, or we may write j0 plus sigma, the complex conjugate of electric field intensity. So first, uh, first the let's write the scalar product between H conjugate and this equation. Okay. Uh, no, not this, but we need to take the scalar product of H complex conjugate and this equation. Or let me with this equation. And what we will have H complex conjugate dot rotor of E. So H conjugate dot rotor of E is equal to minus J omega mu. So minus J omega mu H dot H complex conjugate. And similarly we write the scalar product between, so similarly we write scalar product between electric field intensity E and the last equation, which is this equation. What we have, E dot rotor of H E dot rotor of H will be equal to J complex conjugate minus so minus J minus J omega epsilon E. So minus J omega epsilon dot E. In this case without complex conjugate. Now, these two equations may be combined These two equations may be combined using the vector identity where, so let's see this term H complex conjugate dot rotor of E according to the vector identity is equal to is equal to E dot the rotor of H plus E dot rotor of H plus yeah, the divergence of E cross H complex conjugate, and if we move it to the left hand side, what we have, H complex conjugate dot rotor of E minus E dot rotor of H will be equal to the divergence of E cross H. So this first term is this, the second term is this, and their difference gives us this expression. Or if we subtract from the first expression the second expression, we will get this answer, and we may apply it in J. We get the divergence of E cross H will be equal to J omega will be equal to minus J omega mu H complex conjugate minus J omega mu minus J omega mu H complex conjugate minus EJ minus E dot J plus J omega epsilon J omega epsilon E dot E complex conjugate. And if we rearrange the terms, we get, so E cross H, and if we factor out J omega, we have epsilon E dot E complex conjugate minus mu H dot H complex conjugate and minus J multiplied by E, or E multiplied by J. So the first two terms on the right hand side represent the electric and magnetic power densities respectively. This term represents the electric power density, and this term multiplied by this term represents the magnetic power density. The third term represents the input and dissipated power densities. The last term represents the input and dissipated power densities. Using the ideas of transmitter and receiver cases, which we discussed in the last lesson, the term E dot J complex conjugate can be replaced by sigma E dot E complex conjugate in the case of receiver, and can be replaced by minus E J complex conjugate for the transmitter case. Okay. As we have already done in previous lesson also. So in order to write these terms of power, or better, these terms, okay, all these terms are written in terms of power densities, and in order to write all this in terms of power instead of power density, we should integrate our last equation, which is this. We should integrate this equation over the volume V. So what we have, integral over the volume V of divergence of E cross H complex conjugate dV is equal to, so J omega, the integral over the volume V, epsilon E complex conjugate minus mu H complex conjugate dV and minus the integral of V E multiplied J0 complex conjugate dV minus E multiplied by E complex conjugate dV, but here should be sigma. And using the divergence theorem for the left hand side, we may write that integral over the closed surface S of E cross H complex conjugate of ds is equal to this expression. Okay, let me copy instead of writing all this. Okay, where in our case where J0 indicates a source current density. Okay, the left hand side is the complex power flow through the surface S, and which is enclosing the volume V. The first term on the right hand side is the reactive power in the volume. The second term on the right hand side is the complex source power, and the last term is the dissipated power in the volume if dissipation occurs. Okay, you may remember from the previous course that there are the complex powers and active powers. So the first term on the right hand side, which is this term, is the complex not complex power, sorry, is the reactive power in the volume V. And the second term, which is this, and the second term is the complex source power, and the last term, which is this, is the dissipated power in the conducting media if dissipation occurs.